You are here, perhaps, because you would like an AI to tell you what is wrong with your computer. And I am here to tell you that that is tricky. So I am Austin Parker, and I do a lot of things. I wear a lot of hats. Today, just this one, but I'm part of the OpenTelemetry GC. I'm a co-chair of this event. I'm an author, speaker, da-da-da-da-da. I'm also an alignment maximizer. Everyone loves, who's here? Who likes alignment? Yeah, alignment fans in the crowd? Cool. So lately, I've been focusing a lot on AI, like some of you maybe have as well. I've been working on our AI team at Honeycomb since about February, March of this year, helping build out some of our AI features that we've recently launched. And I'm not here to talk to you about those. What I'm here to talk to you about is all of this. So what we're going to go through today is, first off, who here, just show of hands, who here is like using AI in their work? Like you're using Cursor, you're coding, Claude, whatever. Who's building AI features? AI powered features? A couple of you? Okay. So for those of you who are already familiar with this part might be a little bit of a very brief overview, but it's hard to talk about AI without really talking first about what is a language model, what is a large language model. And I don't have time to go into the details. What we're looking at here, this is a visualization from a website called bbwycroft.net/LLM. And this is a visualization of a very, very, very simple transformer model called NanoGPT. It has 85,000 parameters, and it is taking this sequence of 6 letters and sorting them into alphabetical order using transformers. GPT stands for Generative Pre-trained Transformer. And whenever you go to ChatGPT or open up Claude Code or do anything, something a lot like this times about 1 trillion is happening very quickly. And the result of that is whatever text is getting spit out, right? Whatever the next most likely token is. It's a lot of math, and that math is then taken and sort of trained or aligned or massaged or however you want to say it into some sort of model that we actually use, right? The base thing that happens in that GIF, in that video of everything getting converted into numbers and vectors and transformers and all of this fancy ML that I don't understand very well. I don't need to understand it that much because now we have these models like GPT-5 or Claude, Haiku, Sonnet, whatever, right? We have these models that have been taken and sort of steered to do helpful things for us, to answer questions, to write code, right? And what's really fascinating about that is that what we have kind of found as people studying this have found that that actual act of taking that base model, that next token prediction model, and turning it into an instructor or a chatbot or whatever, does a lot in terms of enabling certain capabilities, certain emergent behaviors come out of that. And an important thing to think about when you are thinking about LLMs and when you're thinking about AI is remember that models are not reading text. They are not looking at a picture, right? What happens is text is transformed into a set of tokens. And those tokens are what you see on the right here, right? This entire sequence of numbers. These are integer IDs, and they are indexes of a vector embedding. And that vector embedding is a single high-dimensional vector, which has thousands, perhaps hundreds of thousands of components in it, and that vector represents the semantic location of whatever that token is in sort of the model's latent space. Another interesting thing is the content, the semantics, are actually separate from the position. These are actually tracked separately. So even though we see this token comes from that token, that token, that actually doesn't matter so much to the model. The positions are separate. those vectors are then processed by going through all those transformers and turns into, at the end of it, it spits out, okay, based on all of these tokens in the sequence, what is the next most likely token? But when we train them, weird things happen. Weird things like this. So what you are looking at is very recently, Anthropic, I believe, published a paper showing how do models understand visual concepts. And they took a bunch of SVGs and pictures and kind of fed it through there and said, okay, this is a bear, or draw me what you think a bear looks like in SVG. And then they were able to look at it and kind of extract, these are stable concepts. They could pull out the concept for, mouth and say, now take that concept and draw it as ASCII art. And they could look and see sort of the same parts of the model lighting up. And this is like really super fascinating because it kind of shows, it demonstrates that, okay, like when I talk about a concept like mouth or ears or whatever, that isn't just like some arbitrary thing, that's an actual semantic concept inside the model, and then the model can generalize around that. There's another kind of interesting side note to this, which is, have you ever asked ChatGPT to add two numbers together? You say like, what's 5 plus 5, ChatGPT? Scientists and ML researchers have studied like how does the model do that, because 5 plus 5, the next most likely token is probably an equal sign, right? They've gone and they've done some studies on this. They found that actually models kind of develop the ability to do addition through trigonometry. I will give you a link to this. It's a fascinating paper. But this is all cool, but it's not very useful. It's really neat that we have, these huge gigabrain quasi-thinking machines that give us cool non-deterministic output to predict the next token based on the sequence of tokens up to that point. But that is not exactly like going to, revolutionize how we do our job. And it's also not going to fix your computer for you. To fix your computer, or to even tell you what's wrong with your computer, you need to take that model and then give it the ability to kind of interact with the world. And we do this through agents, right? Our model itself is a helpful set of bits that kind of corresponds to, some lossy representation of all encoded human knowledge up to this point. And if we take that and we tell it how to use tools, and a tool can be anything from read the contents of a file and replace it, to here's how you use a web search, to hey, here's a calculator. Now if someone asks you to add 5 plus 5, you don't have to guess or do it in your head. You can just ask the calculator to do it for you, right? And what's important to keep in mind here is that agents are actually really, really, really simple. Because all the agent is taking an LLM, putting it in a loop, and giving it an environment, and then letting it kind of do whatever, right? This is from a talk that someone gave a little while ago, which is a play on the sense that a model or an agent is an LLM using tools in a loop. This is saying, oh, it's wrecking its environment, which is true, right? Because if you just take an agent, you take Claude Code, you take whatever, you throw it in a Docker container, and then turn off all the brakes and say, hey, go do something, it will gladly do something, right? It'll delete files, it'll create files, it'll make itself so it can't run anymore. Agents have very little sense of self-preservation. And we don't do this as a matter of course because we understand that giving these agents a bunch of autonomy is actually really dangerous, right? Like if you think about your job, when someone comes in fresh off the street, first day at work, do you give them the root credentials to production database? Probably not, right? You don't, we have ways that we build up implicit trust in people's abilities over time. Even people that come in that are like, hey, maybe some of you here think like, I'm really cool and smart and funny and handsome and would like to work with me someday. Would you trust me on day one with like root creds to your AWS account? Probably not, you shouldn't, right? Because even with that implicit trust of like, oh, so-and-so's whatever, like we just don't hand out these kind of things. We have systems, we have permissions, we have all of these processes and tools and ways to kind of encode explicit restrictions on our environments to make sure that either people having a bad day can't, completely blow everything up, or simply to ensure that we can continue to do whatever it is we're doing. And that autonomy, that you get, that I would get coming into your job and working over the course of weeks or months or whatever, we can think about that a lot of ways. The same with the robot, right? The same with our agents. Like, we shouldn't expect to just have an agent come in and say, oh, here's my repo, just go ahead and start making changes, right? But we do. we actually trust these things a lot, which is honestly kind of shocking, right? The amount of autonomy that we cede to an LLM agent, and I'm as guilty of this as anyone, right? Like, the great thing about agents is it lets you be lazy. I can just say, instead of having to go through and read a bunch of PR comments, I can just be like, hey, Claude, can you look at the PR comments here and then summarize them for me? And if you want to be really lazy, you can then say, okay, now I want you to reply to them in my voice. Little hack right there. And the reason, I think the thing that we miss a lot, or as an industry, is that autonomy and knowledge are very linked, right? We move from this sort of implicit to explicit threshold, and to go back to what I was saying about you don't give someone their DB creds in the first day, over time, when someone starts out at your job or whatever, you start out only having this explicit knowledge. You only know what's written down. You only know what's in the onboarding docs. And then as you land PRs, as you continue to kind of build trust and make friends and influence people and whatever, we start moving over here more, and now you get trusted with those more implicit things because we trust that you have picked up all of the knowledge that suffuses in our organizations about how to actually do stuff without burning down the house, right? When I was very small, I was told, you can't use the stove because you will hurt yourself. That was true. I would have hurt myself on the stove. I was like 5. But I was also told as I was getting older, and it's like, okay, you are now trustworthy enough to make your own food if you're hungry. You don't have to come and bother mom every time you want something to eat. Great. So there I was one day, a small lad of 5 or 6 or whatever, and I wanted soup because it was cold. And so I was like, wait, crap, I can't use the stove. To make soup, you have to put it in the pot and put the pot on the stove and turn it on and let the soup get hot. Dilemma. So as any enterprising small child would do, I realized very quickly that the metal soup pan had a handle that was attached via a screwdriver, or had a screw on it. And while I was not allowed to use the stove, I was allowed to use the microwave. And that's the story of how we got a new microwave. And that's what we're doing every single day with these robots, right? We are all somewhere on our path to getting a lot of new microwaves really quickly. But I had the explicit knowledge, right? I had all the explicit knowledge and facts of oh, I'm hungry, this is what I can do. Oh, I want soup. Oh, right, all this stuff. I lacked the implicit knowledge of you shouldn't put a metal pot in a microwave because I didn't really understand what was going on. And we see this all the time in the industry, right? When you think about the types of data that we care about when we're doing things like debugging prod, or we're asking questions about data, we have these really big categories of, yes, there's all this stuff that's explicit in the telemetry, right? There's all this stuff that is explicit about our code style that we can kind of tell an LLM, hey, go look at this and mirror and pattern yourself off of this. But so much of what is really important in debugging and in SRE sort of work is this stuff on the right? It's knowing, hey, we started a POC with this new big customer, and there's a ton of stuff flooding in, and that's going to produce slightly different patterns. Or we know that it's getting towards the end of the year, and we see usage go up, and we expect this to spike, right? We know that different teams have different priorities, and we can ask someone on Slack, hey, so-and-so needs to kind of run this a little hotter because we have to do this demo or whatever, right? There's a million things that go in this implicit knowledge, and this is something that human beings, that our brains are extremely good at coping with as social creatures. And it's not, I don't want to say this is some oh my God, AI can never do this, because I don't think that's true. I think that, I think the fact, there's nothing about this implicit data that is special. It's just data, it's information. We are just not optimized as people and as organizations to make this implicit explicit. And if we want to, and if someone is sitting there thinking like, oh, we don't have this, we don't need implicit data in how we run our system, then you are lying to yourself, because I assure you that you do. And you probably just don't even realize what it is. Even the biggest companies have a ton of, that are the most run booky in the world, have a ton of implicit knowledge that goes into their operation. And this right here is why all of this is so hard, right? I've spent, again, 6 months or so working on this. And the real world is full of messy situations like this. Real data is full of mess. I want to go through a couple of, we're getting into fun chart and graph times, so let's go into it. There's a ton of data. This is a sample, this is a kind of a representative slice of traces that we saw. I pulled it a few weeks ago, over about 24 hours. It's not every single one of our customers, but it's enough to kind of give you an idea of the distribution. The median trace that we see, 200 attributes. P99 has over 40,000, which is a lot. Single trace can be 50 to 500 kilobytes or more. The biggest traces that I saw in that window were around 20 megabytes, right, for the complete trace. And it's really not cheap to process any of this stuff. If what I've got here in this JSON, and this is a snippet of just one of our internal spans. And we're a little idiosyncratic compared to some of our users, our customers. We have a lot more attributes on average, but it's not so dissimilar in terms of complexity if you put it against that distribution I showed. Taking one trace, and putting it into an LLM and saying like, hey, analyze this, is really, really, really expensive at scale. Like, you're talking about 300,000, one of these came out to about 300,000 tokens, which is dirt cheap. That's less than a penny in certain models. But there's several issues that you kind of see. The biggest one is around context windows. So if you've used Cursor or Claude or anything, you're familiar with the idea of exhausting your context. Oh, started a new chat, I've ran out of memory. Most tools out there in the market today have a working memory around 200,000 tokens before you either have to compact or clear the session, start over. And that gives us kind of a good baseline to think about what should we actually be putting in. Our average actually does fit pretty easily, like 25,000 tokens more or less. But as you go up and as you get to your outliers, suddenly you could feed in like one of these P95s and still have a little room to chat, but you can't even get some of the biggest ones in there, right? Your P99, your max, will just blow out the context window. And this is what we saw actually a ton early on in developing our AI tools, our MCP servers, is that it would work fine for the demos, and then it's like, oh, someone would go in and say, hey, let me see this real world thing, and it would try to pull way too many tokens back and just fall over and be like, and fail. And then because it pulled more tokens than it had room for, you have to reset the context, and it would just keep trying to do the wrong thing over and over again, because as soon as you reset the context, it loses all of its working memory. So really challenging to take individual traces and put them in and try to get anything on the other side. So what if we aggregate this? That's what we try to do generally anyway, right? Looking at one trace is great for sort of debugging, but if you're trying to operate something at scale, you want to look at all of these traces together. But unfortunately, aggregation is not magic either. Again, we're dealing with tokens and not characters. And we have to think about how are we presenting that aggregate to the model. Most people reach for JSON because everything understands JSON, right? And it's good to do this because it does reduce the amount of data that we send. We go in and say, all right, let me calculate these across my dimensions and send in a little blob of JSON. Comes out to a fairly small amount of tokens. But that's only good for the aggregates. What if I want to see the change over time? Now I have a unique series for each aggregation. And if I only have one breakdown, that's great. But if I have two, now I have quadratic complexity, and my amount of individual repeating fields goes up really, really heavily. Even in my best case scenario, I'm looking at about 122,000 tokens for a simple time series, for just one time series across one dimension, right? And that puts us back into our sort of our danger zone of, by the time we've put that into the agent context, we're not going to be able to really do anything with it without doing a lot of compression steps. So that's less than optimal. Can't really ask a ton of questions without running out of room and having to start kind of from the beginning. So what if we get more compact? JSON is great for machines. It's very easy to read and parse because it has a lot of repeating fields. What if we do something like this? What if we do an ASCII table? At our aggregate level, not a huge difference. We're talking about 70, 80 tokens. One thing to keep in mind, though, is that when we are sending this sort of like columnar data in, we actually have a lot more efficiency because we're not repeating so many fields over and over, right? We present this sort of stuff in a column-oriented way rather than a row-oriented way, and that does help quite a bit. But then you get into the real fun stuff. This is the time series that took 122 character token, 120,000 tokens, and I converted it into an ASCII line chart with a couple of interesting bits of metadata, and it got down to 372. And would you believe the model understands this really well, actually. It is able to interpret quite a bit, the rise and fall of the graph. It's able to interpret quite a bit of what's actually going on here. So we get 95% reduction in tokens, which is great. So let's look at how that works out in practice. I've been doing some experiments with this. I want to set it up. I'm not, unfortunately, going to release the repo with all of these things, but I am going to tell you how you can replicate this for yourself. And the reason why is because, well, this is about the only proprietary thing in AI these days, so sorry. But I am telling you the methods, so you can go and do this by yourself if you like and try to reproduce it. So I have 3 different aggregate plus series query results. Simple, try to get a variety of use cases. We have just a simple count. We have some counts with multiple aggregates in multiple dimensions. And questions for all of these things like, hey, which one of these is the biggest? Where was the spike on this graph? Stuff that's all like really true, false, really easy to get. We also feed in traces. So we kind of try to get each of those buckets. We have the small, medium, large, and very large. And they're all the traces that we send in are more complex than sort of the average that we see for customers. So the other thing that we do is we take these and then we have a transformer, a library that takes those raw results and then parses them into a variety of different output formats. So we start out with the raw JSON, and then we have one plugin that turns it into markdown text. We have another that turns it into XML. We have another that turns it into these sort of ASCII tables that you see, right? And then for each of them, we have a set of questions that look like this. We do very deliberately don't do a lot of steering or cheating in sort of the prompt. Literally everything gets sort of the same system prompt of you answer honeycomb query searches. I will say, like saying honeycomb query searches does bias things a little bit because that does sort of point the LLM towards you're working in honeycomb, and the LLM does know what honeycomb is, or the LLM knows what honeycomb is, so it kind of knows how to interpret our query result syntax. But I would say if you were going to do this in a different tool, you should say like, oh, this is Prometheus time series, right? I don't think it impacts the results. I think it's accurate, especially considering that the way we tell people to consume this is either through our agent or through an MCP server that says, hey, this is a honeycomb query result. So the user prompt is, again, very straightforward. It's here's whatever. We inject the input data in whichever format and then ask it kind of a yes or no, true or false question. And we do about 6 questions each. The important thing is that all of the answers can be evaluated with a simple heuristic, so we can be really precise about saying like, yes, it gave the right answer, no, it didn't give the right answer. And what did we find? So here's our top level results, right? We have, this is across all of the query questions, so the first set of things, this isn't traces. But we get some highs of about 90, almost 90%. I think like 88 something, 88 point something for the GPT series, and then Sonnet 4.5 comes in a little lower, Gemini comes in a little lower, and then your like smaller models, your Claude Haikus and your Gemini Flashes come in, kind of at the bottom. Although I will say all of these are better than random chance, right? Thank you. If we look at it by format, we see some other interesting things. So actually, Markdown, very high. I think a lot of people's assumption is like, oh, models understand JSON really well. Turns out they understand Markdown a lot better. So, and then we see XML, ASCII table, Markdown table. The honey_ASCII things are the format that we use for our AI tool output. And when I showed these to people, internally, their first reaction was like, wow, that seems really bad. You don't have 100% accuracy for these very simple questions. And I'm like, yes, that does sound bad. Let's talk about why it's not. So here's a breakdown for GPT-5 Mini. Very modern, pretty affordable. And we do get into, across these kind of top 4, they're all at the same level pretty much, right? Regardless of format. And there's not a huge, you don't see a huge dip until you get into like the honey ASCIIs. And the reason why is because those are highly compressed formats, right? Those are the, a lot of those are, we've taken all of the series data and we've turned it only into visualizations, and there's no actual series points. A lot of the failures that we see on both of these are fairly similar. That's why there's not a ton of variance between them, because what happens is quite often you will get like off by 1 errors where the model's like a little high or a little low. And sometimes literally it's off by 1 when you've asked it to like add 2 categories of things together. The other very similar problem is we see a lot of sort of things are off, but not by an order of magnitude. It's not like, oh, this is twice what it should be. It's like it's off 100 or 200, one way or the other, but it's not off so much that it changes the result, like the semantic result, I should say. And the last thing that we see pretty consistently is everything has trouble with timestamps. Holy shit. No model can tell time. They are aware of time, but if you ask them what day it is, don't trust them. If you push on these pretty hard and you kind of like push leaners out and you say like, okay, well, I asked for the full ISO timestamp and it forgot the seconds part. You do get you get better results, right? Like it does take some of these from like this. If we had said, okay, anytime it gave us a timestamp, as long as it got the day and the day right, maybe we ignore the year or the seconds part, then that would push us for haiku up into the mid-80s, I would say. So what about traces? Traces actually really interesting because we see higher accuracy overall across all of our models. And we see higher accuracy by format. This trace ASCII gets us almost 100%. And you might be asking yourself, what is trace ASCII? Well, this is what trace ASCII is. So I tried a lot of different things. I gave it a picture. I gave it SVGs of a trace. And I found that the best thing is actually this. You topographically sort your spans, and then you literally like stitch them together with ASCII characters. And the model understands this. What's even funnier is it understands this so well that you can give it this and then ask it for .viz or some other like formal way of representing a graph, and it will give it back to you. And it's accurate, which is wild. And this is the takeaway. This is really the important thing, I think. Because what we are doing, because remember, the whole point of this exercise is figuring out how to balance the accuracy versus tokens. Because if we we can have high accuracy by giving it just raw data, but it isn't very useful because we start running out of context. We start running out of the context window. So let's look at where we stand. Over here at the very, very small token side are ASCII formats. We have stripped out quite a bit of data from those, but it gets us down in the hundreds of tokens per input. In the middle, we kind of have Markdown. CSV tends to work pretty well. Although again, we're getting up into the token count here, and then out at the end we have our XML and JSON. So highly repetitive, a lot of duplicate fields, a lot of duplicate data. So I think the first thing to take away is when you're talking about aggregates, when you're talking about these things, never ever don't use XML, don't use JSON. You are paying a huge price, and if you notice where our lines are, we're not getting like significantly higher levels of accuracy from those more custom formats. For traces, it's a little different. Our ASCII is far and away the leader here, even beyond XML and JSON. So do the ASCII thing. And what did we learn from all this? Well, 100% accuracy, very, very difficult to get. And kind of surprisingly is that you would expect that the more verbose things would be more accurate, right? Because you haven't lost any data, and we found that that's not necessarily true. The trade-off isn't nearly as bad as it's saying. Is not as nearly as bad as it seems. And the third thing that was very surprising is that this doesn't necessarily translate to improvement on sort of multi-step evaluations, because yes, it's great that you can send all this stuff and ask it like true false questions, but most of the time when people talk about building agentic AI for observability, they want things like this. So these are our complex multi-step evals. This is, look at these SLOs, look at this data and root cause stuff. This is a snippet of sort of the judgment output for it, but we have gotten we're at 100% on these sort of complex multi-step evals to say like, hey, based on this known data, I need you to go through and analyze it and figure out like what's going on, and then we say it's a good answer if it kind of meets these criteria. And the big thing we see with this is that it doesn't necessarily matter how compact we make it or how many little errors there are. You don't really need that 100% accuracy. It does depend on the task. It depends on a lot of things. But agents are able to like learn from their mistakes, and they're able to correct it. So if the agent does something and it's like, oh, that doesn't make sense, it's able to kind of go and do it again. And you actually start to get much better results by reducing the amount of tokens, because it gives the agent more room to be wrong, and it gives the agent more room to figure out like, oh, I messed up, let me try something different, versus if I'm sending in this really high fidelity data and it runs out and exhausts its context window too quickly, right? So we actually see better results the more we compress the data and the more ways we give the model to kind of pull out interesting things from it. Now, to wrap up, because I think they are going to gong me off the stage soon, I do want to point out, everything I have said here is true as of today. But none of it might be true tomorrow, right? Like, there's a lot more that we can be doing here. Something I'm working on now is like, okay, we've compressed the data so much into these alternate formats. Can we also give the model a raw JSON link so it can download it and then parse it with like JQ or Python, right? But the important thing to think about is something like this. This is from a guy named Ethan Mollick, who blogs about AI. And he made this chart to show, hey, here's the progress in image generation over the past few years for diffusion models. So these are all the same prompt. Otter on a plane using Wi-Fi. And we have February 2022, which is very abstract. And then we kind of keep going from there. And you can see how rapidly like this field is evolving, right? And it's not one-to-one. Stuff that's happening in diffusion models isn't necessarily also happening in transformers or in like text completion stuff. But there's a lot of money going into this, and things are changing really quickly. So it might not be worth it to overfit too much. You need to be fast, you need to be nimble, right? Like, yes, we did all this testing to kind of prove that what we were doing made sense, but context length is going up. Like, we're probably gonna get to 1 million being the standard rather than 200K. Agents are getting better at sort of managing context and figuring out what they can drop and what they can keep. It's all very dynamic. It's entirely possible that in 6 months someone's going to drop a model that is so well trained on Markdown or on JSON that all of these optimizations go out the window, and it makes more sense to deal with the higher overhead of JSON or to figure out how to reparse things slightly to give it more compact JSON. Either way, it's a super exciting, super dynamic time. I would love to talk to you all about this. If you have found anything interesting in sort of the AI analysis of telemetry, we are hiring as well at Honeycomb if you want to come work on this stuff. So hit me up. I am Austin at honeycomb.io. I am on Blue Sky at aparker.io, and you can find me on LinkedIn. So I think we are at time, so I will take questions out in the hallway. But thank you for coming.